Now we're going to talk about how to identify chiral carbons within a molecule. So we've already seen examples of achiral and chiral molecules. If you recall, propane here, shown on the left, has a plane of symmetry about it. So you can bisect this carbon basically and split the molecule down the middle evenly and come up with two identical halves. On the other hand, over here where we had a chlorine, a bromine, a hydrogen, and a methyl group, there was no way that we could draw such a plane of symmetry. And so this was a chiral molecule. And specifically, it's this carbon here that's chiral. So we're going to say that that's a chiral carbon or a chiral center. You're going to see those words used interchangeably. So I'm going to mark this with a star and say that this is the chiral carbon at this position. In order for a given carbon to be chiral, it needs to have 4 different groups around it, because that's going to be the only way that you can't draw a plane of symmetry through that carbon. The only type of carbon that can have 4 groups around it, of course, is an sp3 carbon. So if we want to identify chiral carbons within a molecule, we can automatically rule out sp2 and sp carbons because those cannot have 4 different groups around them. Of course, the other groups that you can cross out, the carbon types, are CH2 carbons and CH3 carbons. Are not chiral carbons because they have too many hydrogens around them. So we are going to cross out the CH3 here, CH2, CH2, and CH2. So now what we're left with is the carbon at this position and this position that we're trying to decide if these are chiral or not. They are sp3 and they're not CH2 or CH3 groups. So let's draw in the hydrogens that are missing, and let's talk about how to decide what constitutes a unique group. So it's pretty obvious if you look here that chlorine and hydrogen are not the same thing, so those would count as 2 different groups. But when you get over here, you have a CH3 group this way, and you do have a carbon at this position. And so we're going to go out 1 atom at a time. And we see that if we were to go in this direction or this direction, we first encounter another carbon atom. So far they look like, okay, maybe they're the same. But if you go out 1 further here, you see that there's only hydrogens. If you go out 1 further in this direction, you encounter another carbon. And so these are not the same group. We can count these uniquely as 2 different groups. And actually what we're counting is the CH3 group is a 3rd group, and the 4th group is the entire rest of the molecule as far as this carbon is concerned. And so this is a chiral carbon. It has 4 unique groups around it. Now let's take a look at this position up here. Let's do the same sort of analysis. We're drawing in the hydrogen that's missing. This time we actually encounter carbon this way, and this way. And so we have to decide if each of those carbon atoms are different or if we're just running into the same thing. And so we have a CH3 group this way. Here we have a CH2 group that has another carbon on it. So those are not the same group. If you were to go out 1 bond further over here, you encounter a carbon. So that's different than a CH3 group. In this direction, you have a carbon that has another carbon this way and this way. So that's also a different group. So indeed, once again, we have 4 different groups. So this is a chiral carbon. And if I were to designate the groups, we have a CH3, an H. We have the whole rest of the molecule this way as group 3, and then we have the whole rest of the molecule this way as group 4. So let's try one that's a little bit trickier. If we try to eliminate some carbons right off the bat, you notice that there is a CH2 that we can cross out. There aren't any sp or sp2 carbons, so all of the other carbons are fair game. So let's take a look at what's left. We have 1, 2, 3, 4, 5 potential chiral centers, and we're going to take a look at this one first. If we were to analyze the groups, again drawing in the hydrogen that's missing, you see that there's an H and an OH, so those are obviously different. In this direction, we have an oxygen that's connected to a carbon, and so this oxygen is different than that oxygen. So those are two different groups. And then finally this way we have a carbon, so that's a different group. So we do indeed have 4 different groups about this carbon. So this carbon is chiral. Let's do this one here next. Again, I'm going to draw in the missing hydrogen, and if we do the same type of analysis, this time we have an oxygen and a hydrogen that are 2 different groups. But if we go in both directions, we have a carbon, and so we have to keep looking out further to see if they really are the same. If we go out this way, they both have an oxygen, so far it looks the same. But when we go out this way, we have an oxygen in this direction and a carbon in that direction. So those are not the same group. You found a point where they differ, and so you can say that this carbon has 4 groups around it, and it is chiral. I'm not going to go through the other 3 carbons. I want you to take a look at those, doing that same type of analysis, and see if you can convince yourself that indeed those 3 carbons are chiral as well.